kind of a medium-sized one today. Well, in terms of like length of class, I hope to get out maybe half an hour early today. If I haven't talked to you about your final projects, this is the time to do it. We'll spend the end of class just going over final projects. Like we'll sit down and talk together. But we have one more big topic before we head off to break. What we call numerical control variables. So last class we walked through using binary indicator variables as a way of sort of separating effects by group. And so we walked through this depressing example of the gender wage gap using census records. I have a real treat for you today. We're going to get into Pittsburgh housing. So we're going to talk about housing prices and then characteristics of houses that are related to housing prices. So this will be a fun one. We're going to do this in an exercise, but I just wanted to show you some pretty pictures. One of them is going to be especially pretty with a interactive little applet in the slides. So our main question is essentially going to be whether housing prices depend on characteristics like the size of a house and like the number of bedrooms and when it was sold. So these are just some of the standard things that you'd expect. Like neighborhood really matters. So where you are in the city, if your house is in Shadyside, that's going to be much more valuable than a house of equal size and characteristics in, like, what neighborhood do we want to pick on? Like Plum. No one lives in Plum. Anyone live in Plum? No. See, anyone live in Shadyside? Okay, maybe no one. Everyone lives in Oakland. All right. So yeah, equal size house in Oakland and in Plum. The one in Oakland is just going to be much more valuable. Our question for today is what the value of an additional square foot is of a house. So as you'd expect, we can just look at the data and pull out a relationship between housing prices and square feet. So I've collected a data set. This is actual transaction records of many, many homes in Pittsburgh, going way back. And as I'm going to show you in a second, we have these variables. So we have like the sale price, we have log price, which is just the natural log of the price of the house. And as we've talked about things like log, we generally want to, the price, we generally want to log them because they scale. And then we have this thing called finished living area. So this is like the square footage of the finished living space. And then we have the year that the house was built. So I've just gone ahead and created some nice figures, but we're going to do this together in the notebook in exercise 5.3. So I have two variables here, and these are the two we're going to focus on most. The first one is finished living area. So on the horizontal axis, I have finished living area, and then on the vertical axis, I have log price. And then all I've done is built a very simple model, just drawing a line through the data. Before we talk about the second one, what do you all notice with this? Like, what are your spidey senses saying to you about this first graph with finished living area? Do you like this model? How many hands for yes? How many hands for no? All right, so I want someone to represent why you don't like this model. Alexis.
I feel like if we didn't have the red line, you wouldn't really be able to tell what's going on. It's very clustered around like the 12-ish.
Okay, so yeah, there's a lot that's kind of packed in right here. And maybe Alexis is saying, like, maybe this red line is sort of leading our eye to a potential relationship. What else, Jay? I'm sorry, say that louder. Okay, so maybe some curvature. Yeah, so it could be that there's like an additional bit of curvature. Definitely, like, we see some extra data down here that we don't see above. Yeah, what else? Yes.
Yeah, similar to what you said, I feel like, I totally don't know, but it's like the opposite of an exponential, a logarithmic
Okay.
graph. I think of that's the first level here.
Yeah, so even though we're using log price on the vertical axis, there's still this kind of curvature to the relationship potentially. What else? There's like maybe another thing that we should be worried about here. What about heteroscedasticity? When I look at this, I see the potential for there to be lots of like, these are essentially outliers. I mean, they're not really outliers, but there's a lot of extra data that's very small. We might see some curvature here. When I look at this, I do see the possibility of a relationship. And as we'll see, the slope is going to be very significant. But my biggest concern when I see this is nonlinearity and heteroscedasticity. There's lots of variability for small finished living areas, where there's not as much variability for larger living areas. So we're going to talk about how we deal with this problem a little bit later. Y'all know how to deal with this? We've talked about this once. Anyone remember? I'm sorry, I never look at you all. Deep apologies. Yeah. So adding a square term would allow us to change the. It would allow us some curvature to the model itself, but it wouldn't directly deal with heteroscedasticity. So the way we deal with heteroscedasticity is we just add heteroscedastic robust standard errors. So this is pretty easy to deal with, and I think that's, to me, when I look at this, that's maybe the biggest problem. Okay, so that's the first one. I've also gone ahead and set up this second model, so year built on the horizontal axis, and then I have log price on the vertical axis. How many of you like this figure, this model? Hands up. Commit to it. Do you like it? Hands up for yes. Hands up for no. All right, someone want to represent the yes answer. Why do you like this model? You like it, why? Sabi.
I think this model kind of represents the trend better because we can see that even though it's really clustered, we can see that it's still like an upward slope trend.
Okay.
While in this one, it's not easy to tell, like Alexis mentioned.
Yeah, so this one, it sort of maybe has like an upward trend on a larger portion of the domain of the model. Yeah, so maybe it's just easier to sort of notice the relationship. What else? Yeah. Nice. So yeah, more homoscedasticity. I would say this is in the ballpark of something that looks nice. Like it's never really going to be perfect, but this is pretty good. What else? Why do you not like it? Those of you who raised your hand, and I know there are a few of you. Yeah, Luke.
I mean, I definitely think it's better than the first one. I think you can see some sort of positive linear relationship. Maybe it's just because there isn't a lot of data prior to 1850
Yeah.
It looks like around 1900. That some of the data is like bunching like downwards, so it might not be linear. I feel like because it's just concentrated between 1900 and 2000,
Mhm.
while it establishes more of a linear relationship than the one on the left, we can't be certain. So it's
Okay.
an improvement.
Yeah.
So it is. We're looking at year built versus living area, but I still think always.
Yeah. So it's not perfect, but it's definitely better than the first one. One thing we could have done, I didn't do this for today, but we could throw out these very small priced houses. Those are, it's like log 2 is very, very small. So this is sort of meaningless house prices. So we could throw those out, and I think that would improve the model. Okay. So yeah, these are things to be thinking about when you're setting up your regressions. Like when we create a visualization, a big part of what it's intended to do is just give us some extra intuition about whether the model is going to be sort of appropriate. Okay, so nice. So we have two things. So just to step out for a second, or step back for a second, we have two variables that are both positively related to house price. So the larger your house is, so living area, the larger your house, the more expensive it is. And the later your house is built, so the newer it is, the more expensive your house is. Okay? Remember our question. Is a larger house, so going back, what's the value of an additional square foot of living area? So are larger houses more valuable than smaller ones? And by how much? Okay, so these both have a relationship with housing prices, and the figure here shows a potential problem with our setup. Both housing size and the year it was built are correlated. So if we try to predict the year the house was built using square foot, we get a positive relationship like this. Someone want to interpret what this figure is telling us? I think maybe flipping the axes might make it easier to interpret. It'd also maybe make the model fit better. Turn to someone next to you and try to interpret what this figure is telling you. And tell them how many hours of sleep you're going to sleep tonight. Or maybe Friday night.
Oh, no, I'm going home tonight.
Okay.
There's slight correlation in your bill, which is going to compromise the factors depends. So there's some like yeah. But I'm thinking she's enough to
Okay, someone want to say what this figure is saying? Savi?
Just looking at the data points, I would say that between like the 1850s and the 1950s, a lot of the houses were made between 0 to maybe 6,000.
Okay.
And then as we move to 2000, it seems that the data points move more towards 8,000 and 10,000.
Okay.
And we see a really significant shift where all the houses just start having, as a base point, just start having a bigger finished living area.
Yeah. So there's, what Savi is saying is like, in past years, like around the turn of the 1900s, houses had a smaller baseline. So the smallest houses are now much larger. So after the 2000s, you don't really find houses that are this small. So we sort of see this shift upward in the size of houses. Yeah, what else? We also just see just a raw correlation. So I've listed the correlation, but you could also list the slope of this relationship, which are mathematically identical, correlation and the slope coefficient. So you can see the later the house is built, the larger it is, and the larger the house is, the later it was built on average. So what does this tell us? Well, if you think back to our first pair of figures, if we're trying to find the value of an extra square foot, we know we can predict the house price using the size of the house, and we can predict it using the age. Both of these two predictor variables are highly correlated with the thing we're trying to predict, which is house price. So this is sort of a problem, right? Like if we're saying, I want to know the additional value of a square foot, is it because it's a newer house? Or is it because the house is larger? Am I saying that houses are more valuable simply because they're kind of fresher, like they're newer? Or is it because the house is actually bigger? So if I were to just set up a regression model predicting house price with the size of the house, I would include some of the effect that newer houses are more valuable. They're nicer because they're newer, and maybe that's what's showing up in the additional value of an extra square foot, simply because newer houses are larger. So what we're going to do is set up a model to account for these things by including not just control variables that are binary categorical, like we did with gender, but we can include variables that are numerical as control variables. This is the figure I will always present. I feel like every class period I present a figure that looks scary. This is the scary figure for today. Always on the fence whether to show this one, but this is essentially what we're about to do. We're going to build models that look like this, using what we call multiple regression, or we could sort of think of this as having a numerical control variable. If we're thinking about the value of an extra square foot of living area, while controlling for the fact, while comparing two different houses that were built in the same year, we can include a third variable. In reality, we have these three dimensions. We have log price on the vertical axis, we have living area on the horizontal axis, and then we have the year that it was built on another horizontal axis. So we have X, Y, and Z. And what we're actually doing is estimating a plane in 3 dimensions. If we were to just look at 2 dimensions, so I'm just going to move this around a little bit. These are actual real data points taken from Pittsburgh housing prices. This is not simulated data. If we just look at these 2 dimensions, the plane is slightly sloping upward. And this is very similar to the figure that we drew earlier. When we just have 2 dimensions, we're just going to draw a line through the data as if the year that it was built wasn't included. So we're just drawing a line through this data, and you remember it was sloped upward. We could also look at the data from this perspective, looking at the horizontal axis of year built. And then on the vertical axis, we have log price. And you can see this one is sloped upward too. So either way we look at it, we're getting sort of this, our 2-dimensional axis is really just a 2-dimensional perspective on underlying 3 dimensions. And so what we actually want to do is compare two different houses that were born in the same year but have different square footage. And then we want to sort of systematically do this for every year. So one thing we could do is just go through and include different intercept terms. So each year it was built, we just include a fixed effect, just a binary categorical control variable for that particular year. Then we just have many different intercepts, and we can check whether the different intercepts are different. But our main question of interest would just be, what's the slope once we've accounted for different intercept terms, one for every year. But equivalently, or nearly equivalently, we could do it this way, where instead of estimating a line, we estimate a plane. This looks scary. You really don't have to see this figure ever again. In fact, I almost didn't show it to you. But for some of you, this intuition will be helpful. If this is unhelpful, just forget I ever said this. If this was helpful for you, that's why I included it. So how do we do this? Well, with a single variable, if we were trying to predict price, we would have log price as our outcome variable, and then we would set up a single predictor variable. But when we have multiple variables, we have sort of this three-dimensional space. We can set up an equation that looks like this. So this is our outcome variable being log price. We have our intercept term. So this is like sort of how high the plane is. We have the slope on living area. So this is like how steep it is in that one direction. And then we also have the year built. So it's like the pivot in the other direction. So this is our 3 dimensions. And this is the model we set up. If you don't like thinking about 3 dimensions, this is the last time you have to. But like I mentioned before, I include the 3 dimensions just to give you some extra visual intuition if that's helpful. It is for me, and it is for some people. The interpretation of these things kind of changes a little bit. There's an additional layer to the way we interpret the coefficients. The null hypothesis is always going to be 0. And we always have a null distribution, which is centered on the truth. And as long as the assumptions of our model still hold, we get null distributions that are centered on the truth and have a normal distribution. So all the same intuition you've developed for where these betas are coming from, sampling from a null distribution centered on the truth, centered on the truth. That's true with these as well. We just have one extra wrinkle to how we interpret these coefficients. Where before it was estimating, so in the first model we were estimating beta 1 as the effect of 1 more square foot. Now, once we have a control variable, we're saying it's the value of the additional square foot, comparing 2 different houses made in the same year. So we've included this year built as a control variable, which allows us to compare 2 different houses in the same year. So the way we say this is holding year built constant. Then beta 2 is essentially the equivalent, but with the variables flipped. So instead of saying the effect of 1 more square, the effect of being built 1 year later, so 1 year newer, now we're adding this condition. So we're saying holding living area constant. So we're comparing a house built in 1990 to a house built in 1991 if they have the same square footage. What's the additional value of that next sort of newness year? So if it's 1 year newer, how much extra value is it? So where before our betas were unconditioned, now we have this extra condition. Okay, any questions here? Savi?
So the last class when we did the gender wage gap thing, did we also use this one to depict the division of the 3-dimensional model?
Yeah, you could set it up in 3 dimensions, but we kind of don't have to. I find it a lot easier to think of it as different intercepts. But yeah, you could sort of, so we have maybe we'll talk about this after class, but you can kind of rotate there's the 0, 1 in the gender direction, and then there's the wage in the other direction. Or sorry, years of education. And then the vertical axis would be wages. Yeah. Okay, any other questions? Love that. Okay, so our question, what's the value of an additional square foot? Our naive estimate is just to draw a line through the data. We have our vertical axis being price and our horizontal axis being square footage. But that's a bit naive. We know that newer houses are worth more simply because they're newer, or we would expect they are. So what we've done without controlling is comparing small houses that are old to some new houses that are larger. So it includes any potential age effect, which in our case, we'd expect it to overestimate the value of square footage. We'd say our estimate using the original model without the controls would give us a beta 1 that's too large. When in reality, we have to account for the fact that newer houses are nicer. So once we include the control, this isolates out the effect of housing, allowing us to compare two houses of the same size or same year. This is a problem with my slides. Let me just show you the problem. So I ran these two models. So this is model 1. This is living area only. So I'm predicting the price of the house using finished living area. And then I have the coefficient here. Turns out to be very significant. So larger houses are more valuable, and by a lot. We'll talk about the interpretation of this in a second. But then the second model I ran, or I should say the third model, where I have living area and then year built as a control, I've gone through and estimated these things. This is a problem with my model. These two estimates round to the same number at this number of digits. Both are significant, but I'm going to show you the actual numbers here. It turns out they're very different. The first model without controls, I've just drawn a line through the data. We're ignoring the problem of heteroscedasticity for a second. We'll come back to this and deal with it in our notebook. But here I have, this looks like a small number, but this is very important, just in terms of sizes. This is like 1 square foot, so the units are very small. We're going to use a different measure of units in the notebook. So here we have 0.000549. Here, this is off by quite a bit. This is, I don't know, what's that, like 10 to 15% difference? Here we have 0.000455. So sorry about the units being so small. We don't particularly care about the actual size of it. In general, the relative difference is pretty different, maybe like 10 to 15%. Okay, and you can just see the two pictures. Once we've controlled for year built, we get a flatter relationship, meaning that age of the house inflated the estimate of the relationship between square footage and price. So we were overestimating the value of a larger house by not controlling for the age of the house by like 10%. Okay. So with the control, we get the sort of the pure size effect after controlling for age. Okay, so here what I've done is plot the residuals. Any good analysis will include a residual plot. And what you can see with the first figure is, you can sort of, we have this line down here. These are just basically zero priced houses. They're like $20, this line here. And you can see that there's real possibility of heteroscedasticity, but you can see the second model is just slightly better than the first one. We've accounted for some of the underlying variation, making the second model slightly better. Model 3. Okay, but still we need to account for heteroscedastic standard errors. All right, y'all want to run this? I have real data for you. This is from Pittsburgh, and we're gonna build a couple models. Okay, so I just wanted to, we were talking about log interpretation last class, and I gave you some wishy-washy answer. So I just have this slide here for you. When we're dealing with log coefficients, essentially it's, we have beta times 100 is the percent change in the outcome variable if we're predicting a log value as our outcome variable. So in this case, each additional square foot increases the price of the house by what's that? 0.045%. So if you increase your house size by 100 square feet, the price of your house is going to go up by, on average, 4.5%, which is that's pretty big. That's in terms of like the actual value of a house, that's substantial. Okay, and that's nice. So that's essentially what we're doing. We've talked through some of this. I included in the slides if you want them. This is really the core kind of thing we do in empirical economics, is make these kind of these estimates controlling for other variables that we might expect to be related. Okay, so let's hop over to exercise 5.3. I just updated the website to include the link to the notebook, so hopefully that's posted. Sorry, this website looks bleak at the moment. So if you click on the notebook, it should open up. Did y'all hear Google just dropped Gemini 3 like 2 days ago? So, wow. Okay, so let's actually add data to the end of this. All right, so I'm just going to import this data, and we can take a look at it. Do y'all love Gemini? I always get a little creeped out by Google knowing all of the things that I write. I don't use Gemini for most of my work. I use a different one. Do y'all know Claude? It's another AI. Okay, so let's just take a look at this. So this is the data set. This is publicly available data on Pittsburgh housing prices. There are a couple of things to note here. So you can see the property zip code. So if we wanted to, we could actually estimate coefficients. We could give different intercepts for each one of the zip codes in the city, which that would be pretty interesting. It would give us sort of a baseline comparing the same house but in different zip codes. Someone could use that as a final project if you wish. In fact, I had a student in the spring semester who used Zillow data to estimate which neighborhoods had changed their housing prices the most in the last couple of years, which is a pretty interesting project. That was one of those examples of a final project that didn't quite fit in the model, the framework, but he was really into it, so I thought that was pretty cool. So then we also have sale price, sale date, and then we have sale price. So this is how much it's sold for. This is the number of stories. We have year built. We have total rooms. We have bedrooms. We have bathrooms, and then half baths. And then we have the finished living area. I created a variable called log price. So this is just the natural log of the price. And then I also created living area 100. So this is just the area of the house divided by 100, which makes it a little bit easier to interpret. We're going to get pretty small coefficients if we just use living area. So I created this one just to make the coefficients a little easier. Okay. Do you want to model some Pittsburgh housing prices? Okay. Love the enthusiasm.
Yes.
Okay. Thank you, Luke.
Sorry. Reaction.
You never need to apologize for enthusiasm in this room. Okay, so I've just included some code here to create a figure. So I'm just going to run this. This is creating two figures side by side of the different areas and prices and years built. But what we might want to do is create a model predicting finished living area using log price. So this is the thing we were doing in the slides. So you can just hop over to the slides. Oh, are the slides not posted? Would that be helpful if I posted them? Okay, give me 1 sec. How many of you are going home tomorrow? Okay. How many of you are going home tonight? Oh, respect. You all live in Pittsburgh?
Yeah.
Okay, nice. So you could find your family house in this data set potentially, if it's in Pittsburgh. Okay, so let's actually hop over. That'll get posted in a couple minutes here. So for now, you can just reference this here. I'm going to copy it over, and you can just follow along in your notebook. So this is just the model 1. So we're only using the living area of the house to predict the sale. So I'm just going to use actually area 100. Just checking who's paying attention. So this is the square foot divided by 100. This just gives us maybe better units for interpreting our output. So smf.ols, and then we have the equation. So if you're just writing this for yourself, this is smf.ols, and then we're just going to write out the equation. Log price squiggle area 100, and then we need to specify the data, and then Gemini knows what to do. Okay, so if you want to write it out, you can do it that way. I'm just going to run this with the copied code. That'll eventually pop up right there if you refresh the page. Wow, Taylor's so unprepared today. Okay, so this is our model. We've already talked about this estimate. This is essentially 5% increase in the house price whenever you add 100 extra square feet. Okay. So we could do a similar thing if we wish to do I have this in the slides? Yeah, model 2. So if we wanted to construct a model 2 predicting age, predicting house with age, so we could look at year built. We could then set up this model. So this is house age only. So here we have an estimate that every year newer the house is, the property value, the value of the house increases by roughly 1.6%. So every year younger the house is, it's more valuable by 1.6%. That's surprisingly large to me. But these are the two models here. So we're running a line through these two. One of the questions we have though is whether living area and year built are correlated. I've already shown you the figure here. You can run this for yourself. But the answer is basically yes. We could flip X and Y if we wished. So this might give us a nicer model. So you can see this is slightly upward sloping. So newer houses tend to be a little bit larger. And then we could build a statistical model of this if we liked. It's not the main question for us, so I'm going to move on to the next part, which is setting up model 3. Whether we can control for age using age as a statistical control in our model. And how does that affect our estimate of the value of an extra square foot? So sorry this hasn't populated yet. So the way we can do that is simply by adding to our model. So here I'm going to call this model both. This will be model 3. This is both year and size. Model both. So we'll have, let's put area 100 plus year built. And then if we run this, this will print off the regression output for our prediction of area, the value of an extra 100 square feet, once we're comparing two houses built in the same year. Okay. So I want you to turn to someone next to you and interpret this coefficient. What is this telling us? We have a coefficient on area 100 that looks like this. We have this is our p-value, and this is our full model. Let's take about a minute here. This is one of the core skills in part 5, is not just setting up these equations for our question, but also can we interpret their results. You'll use the same kinds of intuition as we've been doing since part 3. So we'll take about a minute or two here. What is this telling us?
So for looking at the coefficient for everything, I think we do the concept
Okay, someone want to help me out here? What is this telling us? Or what's the entire output telling us for our question about the value of additional square feet? I've freshly minted 10 lecture points, just ready to go for wrong answers. Someone want to tell me what it's not? Or you can tell me a right answer, just tell me which one you're trying for. Okay.
So if we're looking at the coefficient for the square footage or the area, holding the year built constant
Okay.
for every unit increase in square foot, we're going to see the percentage of the log price increase by approximately 4.55.
Okay. So this is very close. There are a couple of caveats. Maybe I'll say this in a slightly different way. So the first thing to say is that we're holding the area, the year built constant. So we're comparing two different houses in the same year. Then we have a coefficient of 0.04, which tells us that every additional increase in this measure increases our log price by 0.0455. And the way we interpret that is to say every 100 square feet extra, we have a 4.5% increase in price. So we're looking at a log outcome variable. We say there's a 4.5% increase in the price for every 100 square feet extra.
Okay, so we would say like percent increase in the log price.
That's right. Yeah, so we would say, we would not say that.
Because the fact that we're saying percentage, we can say that percentage increase in the price.
In the price,
itself. Okay.
yes. So yeah, this is a coefficient in levels, but the levels are on the log outcome variable. So we can interpret the price directly, interpreting this as a percentage. Yeah, Savi?
I had a question. So you mentioned that the ear hold is going to be constant for this variable. So that means
Yep.
that every time we consider the additional area, we're going to hold the ear hold constant and then
Yeah.
just like flip when we're using ear hold. And are we going to hold?
Yeah.
Oh.
Yeah, that's right. So yeah, so Sabi's question is, what do we do with this coefficient? And this coefficient is the same, or we interpret it in the same way. We say, if we're comparing two different houses with the same size, but one was built 1 year later, we know the one that was built 1 year later has a price that's 1.4% higher. So the value of being built 1 year later is 1.4% in the house price. Yeah.
So it's like saying that, let's say that there were two houses built in, let's say one was built in the 1990s.
Yeah.
And one was built in the 2000s.
Yeah.
So we're going to consider that both of them have the same square feet area.
That's right.
Okay.
Yeah. And specifically 1999 and 2000. So it's
Yes.
1 year.
Right.
Yep. Okay. Yeah, good questions. What else? So this is the kind of model that you'll be building. There's a bit of residual analysis down here. This is deeply important for checking our models. Here you can see our residuals clearly suffer from heteroscedasticity. So what I'm going to do is add, so we can ask control or add robust standard errors. And what this does, adding this covariance type, controls for robust standard errors, it turns out to not matter here. The p-values are all very small. The actual estimates won't change, but it can impact the p-values. Here, the p-values have changed, adding the heteroscedastic robust standard errors. It's just they're still rounded down. The p-values are small enough that we just can't tell with three decimal places. Okay, so nice. So we've dealt with all these problems. This is a well set up analysis. If you were to take this, you can't take this one exactly because you have all of my code and such. But this would be a great final project. You would write this up and then tell me about the value of an additional 100 square feet in Pittsburgh. But this is the kind of analysis I'm looking for on the final projects. We'll do another one when we get back from break. Should we end it here? Don't sound so happy. We have till 3:15, so stick around if you have questions. Nice seeing all of you. Go rest your brains. Work on your final projects. Be thinking happy thoughts about them. Go eat some turkey or tofu if you're vegetarian. That's it. That's all I have. Yeah, Connor.
Are you doing a turkey trot?
I'm not.
That's
I've threatened to do it every year, and I've just never done it. I'm actually going to be out of town, so that's maybe the biggest reason. Are you doing it?
Gone.
Okay.
You just said, I just know you're a runner. So
Yeah, not this year. I'm out of town. Anyone doing the turkey trot? How far is it?
I think it's not for 1 10K or a 5K.
Oh, okay. So, kind of short.